Okay, so in the example we've just been doing, we typed our data in, but obviously most of the time you're importing your data, so you read your data in from the file. You don't want to be typing it all out. And we're going to work with some data here, which is the blood glucose level of two populations, a diabetic population and a healthy population. And we're going to summarize that data and do a little plot of that data. And this is a different type of plot. So you can see some of the things that are different here is that I've got a different type of plot completely. So we use a different geom. I've named the axes instead of them being variable names there. I'm crossing at 0, 0, and I've got this nice legend on as well. So this will give you a chance to learn about three concepts, and I think I'm right in saying that almost everybody knows what a working directory is, so I'll try not to dwell on that too much. So this teaches you a little bit about working directories, paths and relative paths. I'll try and teach you a little bit about the concept of tidy data and how we go about dealing with data in more than one group. So we're working with this population of diabetic and healthy people, or two populations of people and their blood glucose levels. And I recommend in organising your analyses that you always have a folder structure that you use repeatedly. So for example, this is one that I've used for an analysis of RNA sequence data on stem cells. And this is my directory tree. And I've got my project that I created, my new project is called Stem Cell RNA 2019. And inside that, I've got folders called data raw, data processed, figures, functions, pictures, and so on. And I use this kind of structure really repeatedly, which makes it easier for me to remember what I'm doing. So the things to notice here is that I'm actually using a system. So it doesn't matter what your system is, but have one. Okay, so you can try and do things in the same way each time. You want to use names, if you can, that are both human readable and machine readable. So by human readable, I mean they have some meaning to you, so that if I read this, I can tell this is from donor 1 and the date it was taken. And because of the structure, I know that these are all the bits of script I've written, and that this one is importing files, this is doing some normalization, this is doing PCA, and so on. So that makes them human readable. What makes them machine readable is a couple of things. One is that I haven't got spaces. So R can cope with spaces. R has no problem with spaces at all, but it means that you have to use some extra quotes and things in your code, and it's people that get confused with them, not R. R's absolutely fine with having spaces. So I highly recommend that you never use spaces in your file names or directory names. If you want to separate words, use an underscore or a hyphen, which is called snake case or kebab case. The other thing that makes them machine readable is numbering things. So if you number them, you'll force the order. And if you number things from 0 to 99, let's say, you want to left pad that with zeros. Because if you just have a 1, then the next number will be 10, because the number 2 will come after, because a 1 on its own, the next number would be 1, 0, 1, 1, 1, 2, before you got to 2. You see what I mean? So the fact that you've got a 0 at the front forces it to be 02 next and not 10. So I highly recommend being systematic about your naming of things. So we're going to make a new project. So what I suggest you want to do is close this project right now. So if you close the project, you probably do want to save your code this time. So I'm going to click save, and this will start R up for me again. And now I'm going to start a new project. So you want to do a new directory, new project, and this time, because we're working with this blood glucose level data, what shall I call it? Let's just call it health or something like that. So I've called it health, and I'm going to create a project. And R will restart, and it will start up. I've made a new directory called health on my desktop and started R up in that directory. You can't, no, I mean, because things are, you can't, because it's alphabetical basically. So sorry, I'm answering a question in the chat that I've not read out to people. So somebody's asked, can I force R to use a numbering system like 1, 2, 3 to 10, because numbers aren't always pasted with a 0, padded with a 0. No, you can't, but you can rename all your files to R by left padding with a 0. That's what you would do in that case. So I would often, one of the things I might often do when I'm tidying data is the first thing I might do is rename anything that's not systematically named. So we've got this directory, and what we're going to do first is save a copy of the data. And I'm going to set up a directory structure here by just clicking new folder, and I'm going to create a new directory, which I'm going to call data raw. And then click OK. So that will create a new a new folder inside my current working directory called data raw, and that's where I'm going to save the data to. So we want to go to the slides and save this copy of the data from the slide. So you're on slide 54 out of 91 down here. You want to right click on there and then save the link as, and then look for your health folder. There's mine that I've just made. And then data raw, and then click save. So right click and then save to your folder. And then we'll also make a new script file. So at the moment I've just got the console open. I can click on R, the green button to get a new R script, and I'll save this straight away. So save as, and I'll call it analysis again. So there I've got my structure organized for what you might think of as a sort of simplest sort of project you might do, where you just have one set of raw data and one analysis script. Oh, you can actually, if you want to check your data's in there, you can click on raw data and click to see that it's still there. So in order to read the data file in, you use the read.table command. So the dot is just part of the name. So the whole command is called read.table, and we're going to read that file in. And this is the command you want to type or copy to achieve that. So I'm just going to copy it myself. And I'm going to write a comment saying import here, and then put that command in there. So this part of the command is what we call the path to the file. So if I run this command here, and I'll talk about paths again in a little bit. So what I've done here is I'm reading this file bloods into a data frame called bloods. Okay, so that's why it's appeared as a data frame over here. So the output, if you like, of read.table is a data frame. So assign the result of read.table to a data frame called bloods. And there is my data frame with 2 columns of data, one called healthy and one called diabetic. So this data raw part is what we call the relative path to the file. So it's relative to where we are now. So what's a path? Right, so I'll try and go through it reasonably quickly. So the concept of working directories and paths is not particular to R, it's a general computing idea. And it's one of those concepts which is actually honestly not that difficult, but it seems to cause everybody, and I mean absolutely everybody, a little bit of confusion before they've understood it. It seems like it's more complicated than it is, and then when you get it, you just get it. Path gives the location of a file on some file system. So it can be either what we call an absolute path or a relative path. And an absolute path gives the location from what you call the root directory of that object. And a relative path gives the location relative to your working directory or where you are currently. So that's a lot of terms there I've bandied around, but there'll be ones that you're actually all familiar with to a large extent, I think. So an absolute path, these are absolute paths. For a file like we've got here, bloods.txt, this would be an absolute path. So it says where you are from the directory at the beginning. So we've got an actual, from the drive at the beginning. So you've got the actual drive name at the beginning there. So in Windows, it will be like M:, or maybe C:. In Unix, you have a /users, something like that. On the web, it would start with an HTTP, something like that. So all of these are what you call absolute paths. So they actually give the file system from the root, or the top of that file system. A relative path is given relative to where your working directory currently is. So a working directory is where where the using thinks you are. So I'm in R here, and I type getwd, which means get working directory. It tells me that I'm in a folder called health. So when you use projects, your working directory is your project directory, the name of that folder. So if we want to use a relative path, instead of saying the data is in, we could say the data is in this place. So the data we could give like this. There we go. So this would be the absolute path to that file. So it gives it from the C drive. This is the relative path to that file. So we don't have to go right to the root. So if we're in health, we can just go straight to data raw, because data raw is inside our working directory. So this is the relative path. Where is that file relative to your working directory? And this is the absolute path. Where is that file on the system? The reason relative paths are awesome is because if I write this code, and then I send my whole project directory structure to you, when you run this code, it will work. If I write the absolute path, and you try and get my whole directory structure onto your computer, this won't work, because you haven't got users ER13 desktop health. You've only got health. Okay. So because this is relative to the working directory, if somebody packages up all the code, then it becomes reusable. And that's not just for somebody else, that's for you, future you as well. So if you take your directory project off onto a different drive, your code will all still work if you use relative paths. So we've just read this in, and what we've got is 2 columns. It's a data frame with 30 observations of 2 variables. So I've got 30 people, 1 healthy and 1 diabetic. And in both cases, the value we've got here is a numeric. So any data frame is made of columns and rows. The columns are all the same length. The rows should be the separate observations. So if we want to refer to a particular column inside a data frame, I'll just get rid of that now. We need to use this dollar notation. So I can't just say healthy and run that and expect to see anything, because it doesn't know where that is. If I want to see what's in healthy, whoops, let's not do that, let's put it here. I need to make sure I use the dollar notation. So bloods is the name of the data frame, and then I'll do a dollar, and that will then show me all of that data. So if you want to summarize this data in any way, like apply a function to it, like the mean, I need to make sure I use the dollar notation. So doing mean of bloods healthy will give me the mean of that whole column. And if I want the diabetic mean, I can copy that and change this to diabetic. And that's the diabetic mean. So this relies on the data being in different columns. And that's a format that we think of as being as not tidy, to say tidy being a sort of special word in this context. So it's not a very useful form of having the data, because if you can imagine, if you have like lots of different populations, so if we're actually measuring the healthy and diabetic populations in multiple different countries, let's say, or for multiple different age groups, then we'd have to write this command out lots and lots of times to get each of the means. It also makes it very hard to do any kind of analysis or plotting. So how we normally want our data formatted is not so that you've got two observations on one row. So this is called untidy, or it's not tidy, because we've actually got two individuals on one row. And that makes it look like there might be some link between those, when there isn't at all. Data organised in a tidy format only has one individual or one observation per row. And all the other columns just indicate what the groups are from, rather than using the columns themselves to indicate the groups. So instead of having a population in each column, what we normally want to do is have all the measurements in one column and another column which says which group they're from. And there's a great paper, which I highly recommend reading, it's quite accessible, by Wickham and Averick, etc., on tidy data. It has one response per row, and because tidy data adhere to this consistent structure, it makes them much easier to manipulate, plot, and analyse. And most of ours analysis packages assume that your variables are in this kind of format. So does packages like SPSS, in fact. So it says something about the structure of your data in terms of the relationship between variables or relationship between observations. So every variable has its own column, every observation has its own row, one individual per row. This is a comparison here. Let's just suppose instead of having 30 individuals in each group, we have just 3 individuals in each group. So this is the structure we've got at the moment, where we've got 3 individuals, and those 3 healthy in one column and the 3 diabetics are in the other column. This doesn't really say anything about the structure of the data. Whereas if we do this format, we've got one column here which indicates which population it's from, and one column which indicates what the data are. Okay, so even before you've thought about analysing it, it's already more clear what this is. So if you've never seen this data before, you'd guess that that was a glucose measurement for a healthy person or a diabetic person. Whereas you have no idea, looking at this data, what those numbers even are. They're not labelled, as it were. So this is what we call tidy. So we've only got one individual per row. And we can use a function called pivot longer, because we often get data that comes to us in this format, which is also from the tidyverse, to reshape that data. So I am going to restructure this data. I'm going to call it bloods2. Bloods2. And because I'm going to be using functions from the tidyverse, I need to make sure I load that. So I've restarted R when I started a new project. So I will load the tidyverse again. Okay, it's loaded, and now I'm going to start this new data frame. So I've called it bloods2. I'm going to do an assignment arrow, the alt minus, and now I'm going to use this function pivot longer. Pivot longer, there we go. And what this wants is the data frame I want to pivot. So the data is called bloods. It wants an argument that says which columns from this data frame are you pivoting. So in this case, oops, it's all of them. So I'm going to say cols equals everything, which is a way of indicating that. So I can just pivot some parts of the data frame, which is good when you have big data sets, but not useful here. And then the last 2 arguments I need to give it are, what's the name of the column that these column names should go into? So here, it's like, what should I call this column? In this case, it's population. Makes sense. And what's the names of the values? Names to, so that means names of the columns to a variable called population. And values to a column called glucose. So you could call those anything you like. You could give them different names if you want to. And now I've got this second data frame, which is organised in a tidy format. So one of the things that makes this tidy format so useful is that code that's written to work with this data frame with 2 groups will still work on a data frame which is the same in structure but has 400 groups, let's say. So what we might want to do is just look at the structure of this data frame. So what I'm going to do is use the str on this bloods2 now. And what it's telling me down here is that I've got a tibble. So a tibble is just a data frame, really. It's just a sort of modern type of data frame. And it's called tibble because the guy that invented it, if you like, or designed it, is from New Zealand, and that's how he says table. But otherwise it looks just like a data frame. It acts like a data frame. So you've got a variable called population, which is a character variable with the values healthy or diabetic, and you've got a column called glucose with numbers in. So now we've got a data frame in tiny format, and that 100% will make it easier to summarize and analyze and visualize your results in the longer term. So just perhaps I should say that about 90 or 80 to 90% of the work that I do in R is actually getting my data into a format that's amenable to analysis. So actually running analysis takes very little time. Getting it in from its various weird and wacky formats into a form that makes sense is usually a large part of the work that you do. So in order to summarize this data, we're going to use 2 functions from the tidyverse that are both from the dplyr package. One's called group by and one's called summarize. And we're going to use these in conjunction with another tidyverse thing called the pipe operator. So it looks horrendous, but it's really useful. So this is just another operator in the same way, if you like, that the assignment operator, the arrow, or a plus or minus is an operator. So it's a way of getting data to do stuff. And this is the way we summarize. So I'm going to copy this and then I'll talk through it. So this means take this data frame and then, you can think of that as meaning and then group it by population. So that means do separately things for each population. And then summarize by mean. So the first word in there, that mean, I can use any word there. That's a name. I'm free to change it. That mean there is a function name, which means the mean of glucose. So let me run this. And what it's done is output here a tibble again, because it's a tidyverse package, it always outputs tibbles. And I've got now separate means, the healthy and diabetic. So the advantage of this sort of format and tidyverse in general is that this code is completely reproducible. So in the sense that, or reusable, if I have lots of populations in here, whether I've got 100 populations or 2 populations, this code will be exactly the same. The output looks different, but the structure of what you're doing is the same. You're still grouping it by population regardless of how many groups there are. So that's much more reusable than doing this sort of column selection old schooly. Much more useful. Because this is an operation that we might do every single data analysis by heart without having to repeat yourself all the time. So the other nice thing about the tidyverse and this pipe function is that you don't have to use the dollar notation inside here. So normally, if I want to do something with the column in population, I would need to say bloods to dollar population. By using this, take this and then, the group by function already knows I'm talking about the column in that data frame. And the same with the glucose. So this generally makes your code a lot easier to read. This operator here, percentage greater than percentage, the shortcut for that is Control, Shift, and M. Okay, so Control, Shift, and M. And that will give you the pipe operator. So you can read this as take bloods 2 and then group it by population and then calculate the mean. So we get this result here where we've got a separate mean, and it also tells you that it's what kind of number it is. So this just means it's got decimal places in it, and that the population is a character variable. So we can extend this bit of code. So whereas the previous bit of code here, so that bit is ending the group by function, and then we've got the summarize on here, and we've got I've got a bracket there ending the mean, and then a bracket ending the summarize. If we want to summarize in different ways, you want to add something to this summarize set of brackets. So you put a comma between those two brackets and then add what you want to add on. So let's have a look back there. So that's what I've done here. I've added a comma, pressed enter, and then now what I'm doing is counting the number of cases in each group. So let's just do that. So I've got this function here, this bit of code here. I'm going to do a comma between the brackets, press enter, and then R gives me this nice, a bit of space here, this nice indentation to make it obvious, or try to make it obvious that this is still part of the summarized brackets. And I'm going to say n for the number of cases, and count the number of cases is the length, so the length of the variables. So you could put either glucose or population in here actually. You'll get the same number. So there I've got in the output not just the mean for each population, but the number of cases in each population. So if you're finding this easygoing, there's a couple of extra exercises there where you might add extra things in for summarizing that data set. I will skip on some. The answers are in the slides too. What we're going to do now is go straight plotting this data. So I'm going to use here a different, somebody was asking about histograms earlier. I've got a continuous variable I want to plot, so I'm going to use a histogram instead. So I've got a summary of this data. Let's now plot it. So I'm using ggplot. I'm going to say, what's the data I'm plotting? I'm plotting bloods 2. And then I have to tell it what the aesthetics are. So what am I mapping to what? So it's AES, and then we have an X variable. So because this is a histogram I want to do, I want the glucose levels, these glucose levels in this column are what needs to be on the x-axis. And what's going to be on the y-axis is the separate, how many values there are in each category making up the histogram. So because this is histogram, it does that counting for me. I don't have to do it. So I just tell it that I want glucose on the x-axis, and that's enough. So if I was to do that, I get my empty plot at the moment, and then I'm going to add on a geom. So the geom histogram will automatically divide that up into different categories and count them, okay, which is nice and convenient for us. So I don't have to add anything else to that. I'll do the counting myself. So that's the default histogram, and by default it uses a lot of categories, and that's what this warning is down here at the bottom. Is it's saying that it's using bins equals 30. So by default it's splitting this category, this continuous variable up into 30 different categories and counting how many values there are in each one. So that means we've got lots of ones, and it's all very steppy, and there's little gaps where there's no values. And it's because 30 different groups is rather too many for 60 values. So what we can do instead is change the number of bins. So that's what it's trying to tell you here. Pick a better value. So you can either use bins or bin width. Bin width picks the size of the bin, and bins is the number of bins, which I usually find a bit easier. So I'm going to use 10. And now I've got 10 groups, which makes it look a little bit more like a histogram. At the moment, I'm using the variable names on the axes. And I've also got this is all blurred together. So I might want to change that. So to change the outside border of the histogram, I would change this to colour, or change colour to black, just as we did with the bar plot. So a lot of these arguments will transfer to different geoms. So I've got there now borders around there, which looks a little bit more like a histogram to me. And then I want to change the names here. So we're going to use that scale layer again. So this variable now, instead of being discrete, is continuous. So I need to say scale x continuous. And this is giving you some of the options up here, actually. I don't think it's got name in there, but name is the one you want. Name equals, I'm going to say blood glucose. Oops. And then I'm going to add some brackets and say millimoles per litre. There we go. Right, so now I've got a slightly better axis here. And if I want to change the other one, I'll do a plus and add a scale y discrete. Or is it continuous? I think it's continuous, actually. No, it's continuous. We'll see. It'll tell me. Okay. That's capitalized. Okay. So that's what that little bit of code here says. I've changed the number of bins. Okay, so because we've got two different populations here, the healthy and the diabetic, we might want to show those as separate histograms. We don't want to put a fill inside here because that will change the fill for all of them. So if I change this fill to, let's say green, it's going to change the fill of all the bars to a really garish green colour there. And there's nothing I can do inside that histogram to make that do that separately for separate populations. If I want to do it for separate populations, I've got to do it inside the aesthetic up here. So I've got to actually map one of the variables to an aesthetic rather than mapping it to a particular value. So in here, I can say fill equals population. Let's put a space in here. There we go. And that means it's now done a separate colour for each population. So at the moment we've got a plot a bit like this. This function will allow me to overlay them better. So in this default version, I've got the blue population just completely obscuring the red population. I can use this alpha variable to make those more transparent. But instead of it being geom histogram, it's a different geom. So it's a geom density. So this is one of the things I quite like about ggplot, is that it makes it fairly easy to transition between plot types. So if I've decided that I don't want it to be histograms, actually I want it to be density, I can just take that out there. Everything else will stay the same because the variables are mapped to elements of the plot. I'm going to go geom underscore density. And now I've got that plot, the raw plot that we had originally, where we've just got this overlapping nature of the density plots. If I change this now to alpha equals 0.5, oops. So it's complaining here that I've spelled alpha wrong. So at the bottom, I've got this warning message saying it's ignoring that parameters. So most of the tidyverse functions do this. They, instead of just failing completely, they try and carry on, but they just ignore the thing that's wrong. So it's just ignored that and just carried on and done it anyway, instead of just not running. So I can change this here to alpha, run it again, and now I can see the overlay of those populations more easily. So this is one of the things I really like about ggplot, is how easy, or relatively easy, it is to transition between plot types when you're doing data exploration. And you can even have the same things on if you want to. So I can just add on a histogram over the top if I want, which would be a slightly strange thing to do. But sometimes you kind of want to do that when you're deciding how to plot things. So all of the elements of a plot can be customized individually. So at the moment, we've got this plot here, which is, it's not bad looking plot, but you wouldn't want to publish it like this because you've got this strange grey background in and you've got no axes numbers on here. And you can change all that individually to be exactly how you want. But there are what we call themes, which manage a lot of that stuff automatically. I am going to take off my histogram. Run that again, get my plot. And a theme, you add on as a layer again. And one theme, you can see there's a few that are coming up here. I've got several options that I can use. This theme grey is the default, which is being applied now. But I can also apply theme classic, which will automatically format lots of the elements of that plot in a way you might want to do for publication. So it's automatically taken that grey background off, done axes which are have axis lines on them, and so on. We still have this problem with the x-axis that we have to, or the axis gap that we have to alter if we want to, with that expand argument, but otherwise it looks quite good. And you can change all the font size and so on, also in themes. So that's theme classic. It already looks quite a lot like a publication graph. I'll just quickly go over this little bit before we finish up. You might want to do a different kind of plot with data like this, where you have two groups. And that would be to plot the distribution of each plot, not as a density plot, but as a box plot. So here we've got the populations on separate parts of the x-axis and the blood glucose on the y. So in this case, we have to do a little bit more work with our ggplot to change that. So the ggplot bloods to data part is the same, but the aesthetics we're going to need to change. Because now, if we're doing a box plot, we want to have, on the x value, we want to have the population. And on the y value, we want to have the glucose values. Oops. And we don't want geon density, we want a different kind of geon. And that's box plot. I will get rid of those for the time being. I'm just going to comment them out so I can make those so they're not treated as code anymore. And that means that when I run this bit of code, I'll get the box plot and the theme classic will be applied, but these two things won't be. So there's my box plot now, with population on this axis and glucose on this axis, with the distributions plotted. I've also made these different colours by having the fill also mapped population. If I take that out, because you don't really need a colour on there, they'll come out as just black and white.